And we move now to the next speaker. It is Andrii Sotnikov from Kharkov Institute of Physics and Technology, and we are again have a talk about quantum simulations.
Good afternoon. So let me introduce myself. I hope you see my presentation. So I'm from Kharkiv.
Yes, it's okay.
From the Research Institute of Physics and Technology, and also I'm working also part-time at Karazin National University. So first of all, I would like to also thank organizers for bringing such interesting talks together and wonderful speakers. And my talk is devoted to perspectives of neutral ultracold gases, of neutral atoms as universal quantum simulators. I'm also grateful to Igor Datsenko in morning's talks, who also started explaining a bit physics and the concept of universal quantum simulators. So I do not need to repeat some parts of it, but let me also give an introductory slide with the main concept of simulating physics. So imagine you have classical system like LC contour, but you do not have the source of electricity. So how you can study the oscillations of electric current in your contour? Then you bring pendulum, then just shake it by hand and study the behavior and movement of your pendulum as it swings. And if you know that the systems are described by the same differential equations, you come to the concept of the simulating of current oscillations in the system by using just usual mechanical pendulum. And then you go to the idea of Richard Feynman in particular, the concept of quantum simulator. Imagine you have very complex system like cuprate superconductor with many degrees of freedom, and all of them quantum. You have different types of ions, electrons of different orbital flavors, and also having spin degrees of freedom. And how you can proceed in describing this system. With classical computer, you cannot do so because of exponential growth of the Hilbert space of such system. But you can bring another system, kind of maybe more controllable, and with the controllable system where you can adjust any types of couplings like tunneling amplitudes, interaction strengths, or other means, types of atoms, and so on and so forth. You can then try to attack the problem and describe the system properties and engineer and give some valuable predictions for experiments working with more complex systems. And these are words by Richard Feynman, that nature is classical then. And if you want to make it simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So bearing these words in mind, let us proceed and introduce some basic concepts, and then I'll go to some of the research directions we are doing here in Kharkiv. Optical lattices for neutral atoms work in the way that you shine the near resonant light on this atomic system, and because it induces the dipole moment of atoms even in the ground state, depending on the detuning of the laser, you can have then attractive force acting on the atoms. So atoms are trapped in the maxima of the laser potential or in the minima. So they are repelled from the maxima but trapped in the minima of the potential. And if you create it especially periodic way, like by use of mirrors or special adjustment of lasers, contour propagating, you can create standing waves, and in the positions of maxima and minima, you can trap neutral atoms. And neutral atoms act as simulators of electron systems in solid state compound. So these are the concepts, and let me just mention one particular benchmark with these systems. There are many, like observation of multi-insulating states and different many-body phases. But in particular, first of all, I would like to say that with this system, you want to realize the Hubbard model, the most prototypical model, and which continues to be one of the most popular contrivances of theoretical condensed matter physics. With this model, you can then, by adding some more ingredients, describe many body systems. So you have the hopping amplitude, which creates particle on one particular side and annihilates particle on another side. So this is first term corresponding Hamiltonian, then interaction of two atoms. It could be on-site interaction, or if you use some other types of atoms, it can be long range as well. And you can adjust in these lattices number of atoms by adjusting curvature of the external harmonic trap or other types of traps, and adding particles or removing particles of particular types. And with just adjusting lattice depths in the way that you just change the intensity of the laser, you can adjust these parameters like tunneling, like interaction, and other parameters. So in few words, summarizing, you can say that there are many degrees of freedom, but very good control over these degrees of freedom with called atoms. And so this is the benchmark, or rather recent one, with experiment of lithium atoms in Harvard University. So the research group of Marcus Greiner observed prototypic antiferromagnetic odor with neutral lithium atoms, fermionic isotope, in two hyperfine states, up an arrow and down arrow. And in the microscope, you can image even these states and to see almost perfect checkerboard ordering. So spin-up particles are blue, just correspond to blue cells, and spin-down particles to white cells. So, and you can just track how this order just melts down when you increase the temperature, or measure any correlation lens effects, and so on and so forth. And this is quite, it was quite challenging because you require very low entropies. Also, experimentalists work with ultra-cold atoms, but for a long time, the entropy was sufficiently high to observe in situ this type of magnetic ordering. And now experimentalists work also on a detection of pseudo-gap regimes, or types of approaching kind of D-wave superconducting states that are peculiar to the Hubbard model as well. And but in this talk, I will discuss rather other degrees of freedom. What if you add more components and go slightly further from the spin 1/2 system? And the good systems, good objects for that are alkaline Earth-like atoms, in particular ytterbium fermionic isotope or strontium fermionic isotopes, because in these systems you have nuclear degrees of freedom, so half integer nuclear spin in terbium 5/2, in strontium 9/2. So you have different internal degrees of freedom up to 10 in the projection of nuclear spin, but because of the closed electronic shell, so the atoms with the same amplitude. So effectively there is decoupling of nuclear spin degrees of freedom and electronic ones. And if I say about electronic degrees of freedom, usually people mention that in these atoms like ytterbium, strontium, there is very nice feature that there are also clock states, forbidden dipole forbidden transitions, but you can then pump atoms in the metastable excited state with the lifetimes of order of tens of seconds, so longer than duration of usual experiment with ultracold atoms. And you then populate E states in the same manner. So you have two types of degrees of freedom, electronic ones and nuclear ones. And then you can study many things. And in particular, in these systems, you have also spin exchange interaction effects. So atoms with opposite spin directions interact and scatter in the opposite states. So this is analog of Hund's coupling in the solid state materials. And by using this analogy, you can study also phenomena peculiar to transition metal oxides, where the Hund's coupling then sets the physics for such effects like ferromagnetism, or then colossal magnetoresistance, and also peculiar to D-wave superconductors as well. So for D electron shell, it's quite necessary to have this kind of coupling, which you can realize now with neutral atoms of alkaline earth elements. And here is the sketch of different types of interactions in these compounds. So, and then when you have positive Vx kind of exchange interaction, you have then an analog of Hund's coupling. You have also different tunneling amplitudes for one orbital flavor, and for another, it's also quite common for solid state materials. And then you can simulate more wider classes of systems with these atoms. Here we studied, for example, what kind of phases you can observe with our methodology, like dynamical mean field theory. Although we use it on classical computers, but these are predictions are quite original. So we took the system with the characteristic couplings for ultracold atoms of particular type and calculated what one could simulate and which phases, like antiferroorbital phases, like checkerboard ordering of atoms in different orbital flavors on nearest neighbor sites, then antiferromagnetic ordering, like spin up, spin down, then ferromagnetic ordering because of dominant contribution of atoms of one particular type, will spin up, for example, and other specific types. And depending on the number of atoms in a particular orbital state, then these are densities of atoms per site. So by tuning just number of atoms and approaching low enough temperature, then you can enter the characteristic phase and study critical properties of the system effectively. And you can give other predictions with the methodology for this system, what kind of observables you can see, like density profiles in the external trap, double occupancy, but also you can also by means of QCD camera and in situ imaging just track these kind of checkerboard patterns in these systems. And we can also add additional types of special modulations like super lattices, and then we can also mimic Jahn-Teller effects in these solid state materials, quite peculiar for D electron shell and such compounds like manganese oxide and also cuprates with some particular distortions of the lattice. So by just changing parameters of the lattice or by changing number of atoms, you can enhance or suppress like orbital ordering effects in these systems. So this was published 2 years ago, and regarding orbital effects in these systems, but also we did the research in parallel with spin degrees of freedom in these systems. Here I just considered that you have 2 spin degrees of freedom and 2 electron degrees of freedom. So 4 components mixtures in particular, but you can also add more spin degrees of freedom and make the system maybe more complex to some extent. So what if you go now to nuclear spin of degrees of freedom in these systems? And here is also quite a bit of interesting physics. So you just pick particular nuclear spin states, and all of them interact in the same manner with each other because of outer electron shell and interactions which are to a very high degree of accuracy are insensitive to the projection of nuclear spin. And then one can, there is just some phase diagram with more exotic states, magnetically ordered state, valence cluster states, abelian chiral spin liquid states. So quite many types of strongly correlated regimes, depending on the filling of the lattice and depending on the number of flavors used in particular. So here I just mention one type of research with 4 components. When we pick 4 nuclear spin components and do the analysis with our theoretical approaches that we developed in the group. So, and we just write down Hamiltonian. Maybe it looks a bit busy, this slide, but there is not much changes. Just you have 4 components interacting with each other, and you then arrive at SU4 symmetric Heisenberg model in some limits. So you have spin operators between lattice sites, but you now have more extended version, so-called generalized 4x4 Gell-Mann matrices, analog of Pauli matrices, but in this 15-dimensional spin space. And you can then study the effects of spontaneous symmetry breaking of very high symmetry. At quarter filling, at half filling, I will show results at quarter filling, some recent ones. We apply also our theoretical approach, dynamical mean field theory, and arrive at phase diagram where you have temperature versus interaction strengths, and you have some paramagnetic state at high temperatures. So more or less random distribution of atoms among the lattice sites. And then if you decrease the temperature, then you have the effects of spontaneous symmetry breaking. And due to entropy lowering, you need to arrive to more predictable many-body state. And there are also 2 types of antiferromagnetic ordering in these compounds, different type of configurations. And it depends on the lattice dimensionality. Here I will show some results for square lattice geometry, and will comment a bit more phases in the next slide. So as I said, paramagnetic state is just you have 4 flavors and with the 25% probability occupying each lattice site. So it's more or less standard and the highest entropy state. Then if you decrease the temperature or decrease the total entropy in the system, cool down the system, then the system tends to be more predictable. So if you measure the occupation on one lattice site by some flavors, then you need to know something about the nearest neighbor site. And in this state, AFM2, you have the teaming up of 2 flavors against other 2. So and this forms this kind of Chebyshев structure. But this state doesn't fulfill the 3rd law of thermodynamics, because it's still 50% probability to find either green one or red one state on each lattice site, for example. So then you cool down the system and you observe more genuine types of ordering, like formation of plaquette states, where you have some kind of more exotic modulation of flavors over the lattice. And if you have 4 spin components, it's not that easy to distribute them on the square lattice, because each lattice site has 4 neighbors. But if you occupy the lattice site by 1 color, then only 3 colors remain to make happy the system. And the 4th one need to pick up the proper color. And then, but it's still, you can find the arrangement of the colors and make special plaquettes, and we observe it naturally in our numerical approach. And this is the natural state in the zero temperature limit for this particular type of the system. And you can also study some thermodynamics and predict at which temperature and entropy you will observe this kind of exotic types of odor. So this was published half a year ago in our group, and but you can also a bit think about more global perspectives, and this is kind of question of the continuous breaking of continuous symmetry in general, how you then break it and in which residual symmetries remain in the system. And this is also a more general question, even beyond than the solid state applications or high energy physics complications. But it comes from unexpected side, from the cold atoms side, and we studied types of symmetry break-ins and what governs hopping processes or lattice geometry governs, and what is the driving force for the symmetry to break in one particular road or go via branching over other symmetry types. And you can calculate unbroken generators and number of Nambu Goldstone gapless modes in these systems as well. And there are also future prospects studying grand unification theory subclasses like SU5 and how it breaks into SU3 times SU2 symmetric class. And maybe not to overload you with exotic direction. One more example, maybe with yet another possibility, how you can also simulate not only highly symmetric Hamiltonians or very exotic multi-orbital physics like in solid state materials, but also you can even simulate lattice QCD Hamiltonians, lattice gauge theories with cold atoms. And this is quite recent research direction. And it was initiated on the experimental side in Munich group of Immanuel Bloch. So let me remind you schematic QCD phase diagram with quark-gluon plasma, color superconductor phase, and hadron gas. So, and more or less, you can say that cold atoms would correspond to the regime to the right, where you have some kind of quark short for SU4 system, and this is naturally the case. So you have, sorry, and there was problem with internet connection. I hope it's okay now. Then you can have SU3 symmetric atomic mixtures and then they break properly symmetry. But also you can simulate lattice gauge theories in another part of the phase diagram, where you have hadron gas and early universe kind of distributions of atoms. And the usual conventional lattice gauge theories are quite limited due to the sign problem. And then naturally comes that you should use some quantum simulator. And up to recently, there was no good candidate. So to say, maybe I will skip the lattice Schwinger model, but there are certain Hamiltonians and gauge fields and matter fields, and they, for challenges for quantum simulation, it is necessary to implement both matter and gauge fields simultaneously and also respect the Gauss law for the charge. So it's quite untrivial. But with cold atoms, and I would recommend maybe just recent publications by Monika Eidelburger, but I will show only schematically how you can realize with cold atoms, because these are the same ytterbium-173 atoms for muonic species in ground state and metastable excited state. And you create triple well lattices where they can interact at some particular sites. And when you have interacting pair, this corresponds to gauge field, and fermions, G atoms and E atoms correspond then the correlated Hopin fermions, and fermions correspond to matter field. So you then can join these two directions, and by using special techniques, also adding tweezer arrays in the system, you can then control and realize in this way lattice Schwinder model as well. So there are large prospects in these directions as well, I would say. With this, I'm coming to the end. Just acknowledge my collaboration with Adam Mickiewicz University in Poznan, in particular Agnieszka Cichy, experimental team in Munich, with which I exchange a lot of information on current state of the art. And I would like to thank the group. We are working in Kyiv Institute of Physics and Technology, and here are the members, and Vlad Unukovic, not in the photo, but also contributed a lot, our PhD student, to the research. And I would like to thank you for your attention.
Thank you, Andrii. Any questions to the talk, please? Maybe while people thinking, could you tell me a bit just how can you subscribe, especially mechanism when you're telling that it is Young-Taylor deformations? Yeah, it could be how you distinguish between just charge density wave, just displacement of atoms, or it is the same, you mean?
The charge density wave, you can tune also a number of atoms in the system, so you can then well, this yeah, you're right. This particular antiferro-orbital state then has also charge density wave modulation in this particular setup. But with another isotope, you can also exclude you can realize orbital order without charge density wave. So it depends also on the interaction hierarchy.
So you distinguish three let's say patterns of order of your atoms, yeah, of your artificial lattice. It is spin ordering, it is orbital ordering, and just displacement as you, yeah. Is it correct?
Yeah. But I bring distortion artificially. By default, there are no distortions in optical lattices. So, but I can bring distortions by making the well for one particular species for E component deeper on every second side. And in this way, I bring antiferro orbital distortion. So, because on every second side, it will be preferred by the system to be occupied by E atoms. So, and I make it energetically favorable for one particular orbital.
Okay, but also I could say that I maybe never understand where is here the Hubbard model, in a sense that you have some arrangement of atoms, and you have and you see which actually you see which ordering is realized first. Is it spin ordering or orbital ordering, like this? But then you compare with some real system and say that, you see, in the real system we have such order, and therefore it is close enough. But why you call it Hubbard model?
Maybe I do not understand.
No, I mean that from Hubbard model you get the parameters, right, or what? Parameters to simulate.
Yeah, from the optical lattice setup, we know all the intensities of lasers. We can calculate all the parameters of Hubbard parameters, actually.
You mean that Hubbard model is just very good, convenient in terms of parameters, because you need just Hopin parameters. You need these parameters T, U, right, and
yeah, we take it from experiments, so we have one-to-one correspondence in theory and experiment with cold atoms and optical lattices. So we do not adjust. Yeah.
And I also actually wanted to ask just what about this? You have shown these phases along three lines which are present, and antiferromagnetic phases, antiferromagnetic ordering. what actually, what is a result? What you suggest that in the real system, in cuprates, for example, that there is realization of this three, one should expect, or what?
Well, you know that it's not that easy to change the number of electrons in cuprates, for example. You cannot change in large kind of regimes. There are certain dopants when the compound is stable. So to say, at this moment, we only considered 2 orbital states. In cuprates, you have 5, right? So it's more complex. It just I showed that it works in principle, and you can add more ingredients and approach closer to cuprates. But we observe, for example, that in these systems, for example, the orbital order and magnetic order compete with each other. They do not residue at the same parts of the phase diagram. For example, this is kind of important prediction for cuprates as well.
Okay, thank you. Any more questions? Okay, people are tired already and maybe upset that we missed one more coffee break.
Sorry
okay,
for this.
Thank you, Andrei. I stopped the recording.